In this video, I want to review with you the quiz 4 short answer problems. I handed out the questions in class, but I will repeat them here as we go so that you can see how to go through it. The first two are fairly simple. It's just using the formula for a z-score. So the question has two parts. What is the student's z-score? And what formula must you use? So you want to be sure to give both answers when you're answering the problem. So to answer this question, we need the formula for z-score, which is score minus the mean over standard deviation. On a formula sheet, this would look like x minus mu over sigma. But remember, I told you when you read aloud a formula, it helps to understand what you're doing if you tell yourself what the symbols stand for instead of what are they in terms of like mu or sigma or whatever. So this translates to score minus the over the standard deviation. And we can just plug our values right in. So z equals 948 minus 1100 over 44. And I told you I like to work out every single step as I go. So the z-score is negative 3.45. And the problem doesn't ask for this, but I'd like you to think about what does that mean? Well, it means that this student's score is almost 3.5 standard deviations lower than the average score for the SAT. The next problem asks us if a student had a z-score of 3, what would be the student's SAT score? So we need to find the raw score. And what formula must you use? So first I want to stop and think about what does a z-score of 3 mean? Obviously, you don't have to think about this to yourself when you're taking a test, but I just want you to understand it conceptually. So a z-score of 3 would mean that this student is going to have an SAT score that's 3 standard deviations above the mean. So if you calculate your score and it's not higher than 1100 or the mean score given to you in the problem, then you've made a mistake. Okay, so little ways to check yourself as you go through the math. We're going to use the same formula as before. Z is equal to the score minus the mean over the standard deviation. But this time we're going to solve for x instead of z. So we have 3 is equal to x minus 1100 over 44. So we're going to multiply 44 by 3, and that will give us 132. And then we can add 1100 to this side. So the student's raw score is 1,232. You can also double check that, just if you think about it. If you know the z-score is 3 standard deviations above 1100, right, then you could just do a quick 3 times the standard deviation and add it to 1100, and you get, it's all exactly the same, but sometimes people think about it in different ways. In question 3, we're given some fictional scores, and we're asked to calculate the standard deviation and the standard error, and then explain why the standard error and the standard deviation are different. Okay, so for A, we're asked to calculate the standard deviation, and maybe the first thing you want to think about is, okay, what is the formula for standard deviation? And as you go through these videos, try to answer the question before you see me write it down. I'll always pause to give you a second to try and retrieve the information. You don't have to memorize these formulas, but maybe if you have a formula sheet next to you and I say, what's the formula for standard deviation, you can at least check that you are correct in locating it on the formula sheet. So the formula for standard deviation is the square root of the sum of each score minus the mean score squared over the sample size, or n. Okay, and remember that we refer to this amount on top as the sum of squares. Right, so this means sum, and then we're squaring the difference between each score and the mean, right? We're seeing how far does each score vary from the mean, then we're squaring that and dividing it by n. So what I like to do when I solve these problems is draw myself a little chart. So I want to have a column for the scores. I'm just going to go ahead and write those in here. And we have 8 scores, so I just want to double check I got them. 1, 2, 3, 4, 5, 6, 7, 8. And then I kind of draw myself terribly written lines. I'm not good at drawing. My next step is to calculate x minus x bar. Well, I have to know the mean first. So I can't quite finish that step yet. So what I want to do is the sum of scores over n. That's the formula for a mean. And when I add up all of these values of x, I get 426. And I want to divide that by 8. And when I calculate that out, it gives me 53.25. So what I want to do in this second column is subtract the mean from the score. And I'm only going to show this the first time. But this is what I want to do. Okay, so I would literally subtract the mean from the score. And in this case, the value that would go in there is negative 20.25. The next one's going to be 55 minus 53.25, 0.75. Then 54 minus 53.25, 0.75. 65 minus 53.25 is 11.75. 44 minus 53.25 is negative 9.25. Well, I'll show you a little trick. We've already calculated it for this one. Right, so I see up here in this row, there's 65 also, and then 44 is showing up again. So I don't even have to recalculate those, I can just write them right in. And then 66 minus 53.25 is 12.75. And then my end goal is to square these values. And you want to be careful, when you square a negative value, it should come out positive. And so I know sometimes on the graphing calculator, it may not be the case that it comes out positive. So if you notice that to be the case when you're using your calculator, make sure it is giving you positive values. When you multiply a negative by a negative, it's a positive. Okay, so I'm just going to go through and square each of these values. And you don't have to carry this many decimal places. In your exams, I would say go to 2 decimal places past, to the right. But these are kind of easy to write out, so I'm not rounding them yet. And remember, once I get here to 65, it should match up here. These are the same. And these are the same. A little bit less work. All right, and then I can't forget, I need to sum these together. And when I add those all up, I get 1023.5. So now I can take this number and plug it back into my formula for standard deviation. And again, my sample size is 8. And I told you I like to do every single step possible. And this is going to be equal to 11.31. Part B says, assume the population from which the sample was drawn has the same standard deviation and calculate the standard error. What formula is needed to obtain the standard error? So again, you want to be sure to answer all parts of the question, and of course it makes the most sense to start with the formula first. So what is the formula for standard error? Again, try to retrieve it from memory, or at least locate it on the formula sheet. I'll give you a hint. This is how we represent the standard error. Sigma sub m. And it's called sigma sub m because it is the standard deviation for the distribution of means. Okay. Whereas the standard deviation is the standard deviation for a distribution of scores. We talked about this a little bit in class. Okay, so this formula is pretty straightforward. It's sigma divided by the square root of n. So it's the population standard deviation divided by the square root of n. Okay, so you want to make sure you write out this formula so that you're answering the question, and then we can plug in our values. I told you I like to do every calculation separately. Right, and so you could either write 3.99 or 4. Part C of the question says, explain why the standard error and the standard deviation are different. So our standard deviation is 11.31. Right, so we're comparing these two values, and we can see that the standard deviation is much larger than the standard error. Okay, and this has to do with the central limit theorem. So the standard deviation is a measure on a distribution of individual scores. It's going to have more variability than a distribution of means. The standard error represents the standard deviation of a distribution of means, and it should be less variable than a measure on the individual scores. And so we see that in fact, the standard error value is much smaller than the standard deviation. Okay. Question 4 we went over in class, or at least started to go over in class, but in case you weren't in class, or even if you were, I do think it's a bit of a complicated question, so I want to be sure to go back over it with you. So it says, Meehl published a study in the journal Science that reported the results of an extensive study of men and women, in which the number of words uttered per day by each sex were compared. Volunteer participants wore inconspicuous recording devices that recorded their daily word usage. On average, women, there was a sample size of 198 women, uttered 16,201 words per day, with a standard deviation of 1,779.45 words, and men uttered 15,993 words per day, with a standard deviation of 2,224.61 words. Treating the men's data as the population parameters, do the following. Okay, so how do we even know what we are doing with this question? One clue is that the problem tells us to treat the men's data as a population. Okay, and if we do that, that means we have a population and we have one comparison group, which is the women. So, in the event that you are comparing a group to a population, you want to use a single sample t-test. Okay? We have one sample, one group of women, right? Another way you know that we have only one group is that only the women were we given details about the number of participants in the sample. We weren't given that information about men, so they're definitely not counting as a second group that we would need to consider. Okay, the question's not asking us to calculate a t-test, but we want to know what we're working with because we want to develop our null and alternative hypotheses. So if we are, the question doesn't give us a ton of information, but we're comparing men to women. Okay, so given the context of the question, what about the women are we comparing to what about the men? And I always like to write the alternative or research hypothesis first. All right, so if we're comparing women to men, we're given average words per day and standard deviations. So do you think it's likely that we're comparing average words per day between the two groups or standard deviations? Yeah, probably average words per day, right? So our point estimate is average words per day. Okay, and our research hypothesis would be that the average words per day for women is different from the population words per day. And in this case, we just want to remember the population happened to be men's average words per day. So our null hypothesis would then say there's no difference in words per day for women versus population. And in this case, what we really mean is versus men. Okay, so if we're taking average words per day for women, I'm going to just write that down as mu of women. This should be equal to the average for men. And our research hypothesis would be that our average for women is not equal to our average for men. Okay, so that'll come in handy later. So part A asks us to calculate the point estimate for women's words uttered per day. And so this is a little bit tricky of a question because you actually don't have to calculate anything. You've already been given women's words uttered per day in the question. And it's actually already circled up here for you. So the answer to A is just 16,201, which is the average that was given to us in the question. Okay, so part B asks us to calculate the 95% confidence interval around this point estimate. Okay, so again, just describing, we took this sample, this is the mean of our sample, but that's just one sample of many different samples we could have taken. So confidence intervals allow us to express our uncertainty about this point estimate. It's saying, well, in sample A, we got this mean of 16,201. But if you took a new sample, sample B, their average is going to be a little bit different. And we think it's going to fall in a particular range. And that range of numbers is your confidence interval. Okay, if I took from sample C, they'd have a different mean, but hopefully 95% of the time, any new sample that you took would have a mean that's in this confidence interval. Okay, so let's go ahead and just write out the formula for calculating a confidence interval. And remember, I went over in class that I like to think of it generally as your point estimate plus some critical value. In this case, we would be doing a single sample t-test, so it would be a t-critical value, and we'll come back to that in a second. And this is multiplied by the standard error in every case. So this formula for a confidence interval at its foundation never changes, right? We just have to change up either the point estimate, depending on whether we're looking at 1 or 2 or 3 groups when we get to F-tests, or you have to change up which distribution you're looking for the critical value, or you have to modify the standard error because you have more than one group maybe, okay? But in the event we just have a single sample t-test, we're going to modify this confidence interval formula to be point estimate plus or minus a t-critical value times a standard error. Okay, and so where do we get those values from? Well, for our t-critical value, we want to consult a t-table. Okay, so this is the t-table from Appendix B in your textbook. And the question told us to create a 95% confidence interval. Okay, so we know we want to look either in this column or this column over here on the right, underneath 0.05. And so we need to decide, do we have a one-tailed test or a two-tailed test, right? So if your research hypothesis is just that one mean is different from another, if it can be greater than or less than, then we're doing a two-tailed test. If you had a specific hypothesis, let's say that women uttered more words per day than men, then we'd want to use a one-tailed test. Okay, but we don't know which direction it's in, so we're using the two-tailed test, and we want to scroll down this table until we find over here on the left-hand side our degrees of freedom, which is n minus 1. So we had 198 participants, so we're looking for 197 as the degrees of freedom. And you can see the table has a listing for 120 degrees of freedom and then infinity. Okay, and that's just to say that basically once you get beyond 120 degrees of freedom, or a sample size of 121, the t-distribution is basically normal and this critical value remains the same. Okay, so the critical value that we're going to take into our problem is 1.96. And then do you remember our formula for standard error? Right, it's sigma, or the standard deviation, over the square root of n. Okay, so our point estimate for women, 16,201. And I'll fill in the information for our population, which is just the men's information from up here. So men's standard deviation is 2,224.61. And we had 198 women in the sample. So going through my tedious step-by-step work, this would give us 2,224.61 over 14.07. And this would give us 1.96 times 158.11, which would give us, on the right side of the equation, remember I completely made up a silly way to think about this. So basically, our point estimate is in the middle, and we're going to subtract 309 to get our lower limit, and we're going to add 309 to get our upper limit. So 16,201 minus 309.896, and then 16,201 plus 309.896. And so finally, our 95% confidence interval is, and again, you could have gone just to 2 decimal places, and that would have been fine. This is our 95% confidence interval. So we are sure that 95% of the samples that you could take would give you a mean number of words per day uttered by women between 15,800 and 16,510. Okay? I'm just trying to simplify those numbers a little bit. So 95% of the time, the mean would fall within this range. Okay? And our number is directly in the middle, as you sort of emphasized up here. Okay, so now the next part of the question asks us, I'm going to scroll back up here, make a decision regarding the null hypothesis on the basis of this confidence interval. Okay, so what we are trying to determine is a specific value in the confidence interval. And the specific value is the value from your null hypothesis. Okay, so if we scroll back up here to the null hypothesis, we're saying that the words uttered by women are the same as the words uttered by men. So that's 15,993. So the number from our null hypothesis is 15,993 words per day on average. So we need to see, is this number included in our confidence interval? If 15,993 is in the confidence interval, then we can't say our sample is different. Basically, by chance, we got an average number of words per day different from this number, but if you took a new sample, you could get this number. Okay, and so ours isn't different enough from it that a new sample would not potentially have this number in it. Okay, and this is the same as saying if this number, 15,993, is in the confidence interval, then we fail to reject the null hypothesis. All right, so let's check our confidence interval. It ranges from 15,891 to a higher number. So yes, this is in our confidence interval. So therefore, fail to reject the null hypothesis because the population mean is contained in our confidence interval. Okay, now I really like that this question has the next part to it because it helps to see how or why sample size can be so important in your research. Okay, so part D says, to see the effect of sample size, recalculate the 95% interval, confidence interval, assuming a study of 598 women. Okay, so basically the confidence interval, it's the same as what we wrote right here, so no need to do anything no need to do too much extra work. I'm just going to bring that down here so we can see it. The difference now is we need to replace this n with 598. So we have 16,201 plus or minus 1.96 times over the square root of 598. So the question asks us, what happens to the confidence interval when we have this larger sample size? So earlier in our confidence interval, we had over here like 309. That's not the exact number, but pretty close. Okay, so this was with our smaller n. So if the right side of the equation is smaller for our new confidence interval with the larger n, you should be able to guess without doing the math what's going to happen to the confidence interval. So basically over here you're adding and subtracting 309, but over here on the left side you're only subtracting or adding 178, which is like half as large. So your confidence interval is going to be narrower. Right, so we're going to go 178.33 less and greater, which is going to give us 16,022.67 to 16,379.33. And now we're asked to make a judgment about our null hypothesis based on this confidence interval. And remember, the number that we're looking for is 15,993. So is this number in our confidence interval now? Our confidence interval is much narrower. And so now, with a larger sample size, this population mean is actually not in our confidence interval at all. And so now, right, we can reject the null hypothesis, which is to say, conclude that women utter a different number of words per day than men, than the population. And in this case, actually, we can see if we compare the means, so 16,201 to 15,993, we actually could conclude that women utter more words a day than men. Last question. This says, many companies that still manufacture incandescent light bulbs advertise 60-watt bulbs last for 1,000 hours on average. So a product tester bought 30 bulbs, so our sample size is 30. I like to kind of write things down as I go. And burned them until they failed. And he found that they burned for an average of M, remember M is the same as X bar, 1,233 hours, and a standard deviation of 232.06 hours. Calculate the effect size for the difference between the sample and the population. What does this effect size mean? Okay, and so we have our population mean of 1,000. So do you know the formula for effect size? I'll give you a hint. Effect size also goes by the name Cohen's d. D is equal to the mean from your sample minus the population mean over the standard deviation. So this is going to be equal to 1233 minus 1,000 over 232.06, which is equal to 233 over 232.06, which is basically 1. Okay, so that's calculating the effect size. But I'm also asked to describe what does this effect size mean. How do we interpret Cohen's d? Well, Cohen's d is a value that represents how many standard deviations away from the population mean our effect is. And so in this case, if we're going to write that out verbally, this would mean that the 60-watt bulbs are last 1, that's our effect size, standard deviation longer than what is claimed. So basically, Cohen's d tells us how different our sample is in terms of standard deviations from the population. Okay, and there's some conventions for Cohen's d. So a Cohen's d of 0.2 is small, and usually a d of like 0.4 to 0.6 is moderate, and greater than 0.8 is large. But this is really like a rule of thumb. Once you get into research, people don't really use it. But just to give you an idea as you're learning about Cohen's d. Right, so this Cohen's d is very large. Okay, I hope this has been helpful for you. Thank you.